Let us start with similar triangles today. If we take a triangle and zoom out to make a smaller triangle similar to the big triangle. Now, since this is the same triangle but smaller in size, we see that the angles of these two triangles are equal. So, angle A is equal to angle P, angle B is equal to angle Q, and angle C is equal to angle R. But there is something else about the sides that is also interesting about similar triangles. We see that the ratio of the sides is equal. So, AB upon PQ is equal to BC upon QR, which is equal to AC upon PR. So, the ratios of corresponding sides of two similar triangles are equal. Now, let us superimpose the vertex A onto vertex P. And we see that since angle B is equal to angle Q and angle C is equal to angle R, they form corresponding angles for the parallel lines BC and QR. Now, we know that AB upon PQ is equal to AC upon PR. Let us replace P with A. Now, let us apply a few properties of fractions. Let us subtract the numerator from the denominator on both the sides. And we see that AB upon BQ is equal to AC upon CR. So, we see that if BC is parallel to QR, then AB upon BQ is equal to AC upon CR. Now, this result is known as the basic proportionality theorem. So, if BC is parallel to the side QR, then AB upon BQ would be equal to AC upon CR. But here we assumed properties of similar triangles. Let us see if we can prove this result without applying the properties of similar triangles. Let us drop a perpendicular from vertex C onto the side AQ. Let us drop another perpendicular BN on the side AR. Now, let us look at the sides AB, BQ, AC and CR. Can we see triangles that have these sides? Let us also join the diagonals BR and CQ. Now, we can see that AB is a part of the triangle ABC and BQ is a part of the triangle BCQ. Similarly, AC is a part of the triangle ABC and the side CR is a part of the triangle BCR. Now, let us look at the areas of these four triangles. We see that area of triangle BCQ would be equal to area of triangle BCR because they are triangles with the same base BC and these two triangles are between the same parallels, which means that they have the same height or the same altitude. So, we are looking at the ratios of these triangles where the denominators are equal to each other. Now, let us try to formulate the areas of these four triangles. Let us take the base AQ and the altitude CM. So, we see that area of triangle ABC can be written as half times base, which is AB, times height, which is CM. Similarly, for triangle BCQ, we could write half times the base BQ times the altitude CM. Now, let us look at the right hand side. Now, for these two triangles ABC and BCR, let us take the side AR and the altitude BN. So, we could write area of triangle ABC this time as half times base AC times height BN. Similarly, area of triangle BCR would be equal to half times CR times BN. Let us simplify both the sides and we see that AB upon BQ is equal to AC upon CR. It is the same result that we obtained before, but this time we have not used the properties of similar triangles. Instead, we have used areas of triangles. So, the basic proportionality theorem or BPT states that if BC is parallel to QR in a triangle AQR, then AB upon BQ is equal to AC upon CR. Now the corollary of this theorem is also true, that if AB upon BQ is equal to AC upon CR, then BC should be parallel to QR. Let us see if we can prove this. Let us prove this by contradiction. Let us assume that BC is not parallel to QR. Now let us draw a line BD which we know to be parallel to QR. Now if BD was parallel to QR, then by basic proportionality theorem, we can say that AB by BQ is equal to AD by DR. But we are given that AB by BQ is equal to AC by CR. Now look at the right hand sides of both these equations. We can conclude that AD by DR should be equal to AC by CR. Let us add 1 on both the sides. And we see that the numerator is the same on both the sides. And this gives us that DR is equal to CR, which means that D and C are the same point. This tells us that BC is parallel to QR. There is no other point D. To apply the basic proportionality theorem, we need a triangle and a pair of parallel sides. Now, in order to get these two, we could either join diagonals, we could draw perpendiculars, or we could draw parallel lines. Let us look at a few questions. In the given figure, if LM is parallel to CB and LN is parallel to CD, prove that AM by AB is equal to AN by AD. Now these ratios belong to two different triangles. So let us look at them one by one. Let us look at LM parallel to CB. We are looking at triangle ABC. So we could apply the basic proportionality theorem to this triangle and say that AM by MB is equal to AL by LC. Now let us look at LN parallel to CD. We are looking at triangle ADC. So we could apply the basic proportionality theorem and say that AL by LC would be equal to AN by ND. Now let us call these two equations as statements 1 and 2. We see that one of the sides of these two equations is AL by LC, which means that we can conclude from 1 and 2 that AM by MB is equal to AN by ND. Let us add the numerator to the denominator. And we see that AM by AB is equal to AN by AD. Hence, we have proven the result. Let us look at another problem. In given figure, DE is parallel to OQ and DF is parallel to OR. Show that EF is parallel to QR. So we are given that DE is parallel to OQ. So we are looking at triangle POQ. From the BPT or basic proportionality theorem, we can say that PE by EQ is equal to PD by DO. Let us call this statement 1. Now the other thing we are given is that DF is parallel to OR. So we are looking at triangle POR. From the BPT, we could say that PD by DO is equal to PF by FR. Let us call this statement 2. Now from 1 and 2, we can easily conclude that PE by EQ is equal to PD by DO is equal to PF by FR. Or simply PE by EQ is equal to PF by FR. Now the corollary of basic proportionality theorem will help us in triangle PQR. We can see that PE by EQ is one of the sides and PF by FR is one of the other sides in triangle PQR. So by the corollary of the basic proportionality theorem, we can easily state that EF is parallel to QR. Let us look at another problem. The diagonals of a quadrilateral ABCD intersect each other at the point O, such that AO by BO is equal to CO by DO. Show that ABCD is a trapezium. So we have a quadrilateral ABCD and we have to join the diagonals such that their intersection point is called O. Now we are given the ratios AO by BO and CO by DO. We can see a lot of triangles, but we do not have a set of parallel lines. Now recall our tricks. So we could either join diagonals, but we have already done that. Or we could draw perpendiculars, but a perpendicular would not give us a pair of parallel lines. We could draw parallel lines. Now we have to prove that ABCD is a trapezium. So where could we draw the parallel line? There is only one place, the point O. So let us draw a line EF passing from point O, which is parallel to CD. Now we have a set of parallel lines EF and CD. Let us look at triangle ADC. From the basic proportionality theorem, we can say that AE by ED is equal to AO by OC. Now we see that the given equation has the sides AO and CO. Let us manipulate the given equation so that we get AO by CO on one side. So we get AO by CO is equal to BO by DO. Now from statements 1 and 2, we can see that AE by ED is equal to BO by DO. Let us see if this gives us anything. Now AE by ED and BO by DO, they form the triangle ABD. So by the corollary of the basic proportionality theorem, in triangle ADB, we can conclude that AB is parallel to EO. Now this means that AB is parallel to EF. But we had drawn EF parallel to CD. So we can easily say that AB is parallel to CD as well. And hence ABCD is a trapezium.